So, hello everyone. This is a re-recording of my first lecture for the ESE program on higher structures and field theory. So the reason I'm re-recording is because there were some technical issues in the actual live session. So my lecture series in general is about higher structures in algebraic quantum field theory. And this is based on joint works with my friend and collaborator Marco Benini, my student Simon Bruinsma, my student Marco Perin, and Lukas Wojke from Hamburg. So if you're interested in a reasonably up-to-date summary of this work, you can look into our review paper, which is cited here. So the plan for the whole lecture series is as follows. So in the first lecture, which I'm now re-recording, I will introduce an operatic perspective on algebraic quantum field theory and show you how it is useful for doing universal constructions in this framework. The second lecture is about higher categories and quantum gauge theories, so how higher categories are important to deal with quantum gauge theories. And the third lecture is about simple examples and how to construct them by using homological techniques. So let's start with the first lecture. So operats and universal constructions in Aqft. Maybe I should say a few words about what Aqft is supposed to do. So Aqft, algebraic quantum field theory, is a framework which is there for studying quantum field theories on Lorentzian manifolds. So Lorentzian manifolds are these kinds of manifolds which feature in Einstein's general relativity to describe spacetimes. So Klaus Fredenhagen gave in his lecture series a nice summary of Aqft, so I can be relatively brief here, but I would like to remind you of some basic definitions and features of Lorentzian manifolds. So to start with, a Lorentzian manifold is a manifold M of dimension m, small m, which is endowed with a metric, and this metric has a very specific signature. So it is not a Riemannian metric, not a positive definite metric, but it is indefinite in a specific way that at each point you have one negative eigenvalue and the rest positive eigenvalues. So this specific direction here, characterized by the negative eigenvalue, corresponds to a kind of time direction. Now Lorentzian manifolds can be relatively wild, so we will always restrict our attention to so-called globally hyperbolic Lorentzian manifolds. So a Lorentzian manifold is globally hyperbolic if it admits a so-called Cauchy surface, which is a hypersurface of codimension 1 in your spacetime manifold M that is intersected precisely once by each inextensible causal curve. So the causal curves are the time-like or light-like curves, as depicted here in green, now highlighted in red. And how to think of a globally hyperbolic Lorentzian manifold is depicted here. So I draw time going upwards. M is this manifold. I draw it here as a diamond. And it is globally hyperbolic if there is a surface, so this sigma, that is such that each inextensible causal curve intersects it precisely once. So closed causal curves are not allowed in this framework. Now, I take the collection of all globally hyperbolic Lorentzian manifolds and pack them in a category, which I denote by Loc. So more precisely, the category Loc, so the category of spacetimes, contains as objects all oriented and time-oriented globally hyperbolic Lorentzian manifolds. So I would like to have an orientation in order to integrate on them, and a time orientation to distinguish between future and past. The morphisms between such objects in Loc are orientation and time orientation preserving embeddings that are isometric. So these embeddings F from M to N preserve the metric, preserve the orientation, preserve the time orientation. And furthermore, I would like that the image of this map, so F of M is a subset of N, is an open subset, and it is so-called causally convex. So causally convex is the following property. Here is a picture for that. So the image of M, I draw here as a diamond again, and it is causally convex if when I have a causal curve starting and ending in this image, it is fully contained in that image. So what would not be allowed is images of this form, of the potato form, because then I could start in this image and end in that image, but the causal curve goes out and in again of the subset given by the image of the map. So this defines the category log of spacetimes. And I need two more definitions, which I will use later on. And the next definition is about pairs of morphisms in this category. So I consider a pair from M1 to N and from M2 to N. So these are two morphisms, F1 and F2. And I say that these morphisms are causally disjoint, which I write with this orthogonality symbol, if there exists no causal curve connecting the images. So in pictures, M1 embeds in this way, M2 embeds in that way, and between the images you cannot draw a causal curve, which I visualize here by this light cone, saying that there is no light-like or time-like curve connecting the two. So these kind of pairs of subspaces, they play a role of independent subspaces, because in relativity everything is slower or equal to the speed of light. So I cannot send information from here to there and vice versa. So these are the causally disjoint pairs of morphisms. I need another class of morphisms, which I call Koshimorphisms. So Koshimorphisms is about a single morphism, F from M to N, and I say that such a morphism is a Cauchy-morphism if the image of this map contains a Cauchy surface of the bigger spacetime N. So in pictures it looks as follows. I have here the bigger spacetime N, and the smaller spacetime N embeds in a sufficiently wide way. What that means is that it is wide enough to contain a Cauchy surface of N. So when you would draw that not in terms of diamonds, but in terms of rectangles, you would see that this just corresponds to the statement that M corresponds to a subspace of N, which is like restricting the time interval from the timeline to a smaller time interval. So these are kind of very specific submanifolds, which are useful or which play an important role when studying the dynamics of quantum field theories. Because when you have a good concept of time evolution, you can start here and use the time evolution to propagate there. And importantly, vice versa. When you do something here, you can use the time evolution to propagate back into the image of M. So this is the role played by the Cauchy morphism. Now Aqft, and Aqft is now a gadget which links these Lorentzian geometric structures to algebraic structures on the side of the quantum observables of a quantum field theory. So an Aqft is a machine linking Lorentzian geometry to algebraic structure. Now, usually, or say traditionally, people consider C-star algebras to model quantum observables in a quantum field theory. However, for simplicity, I will use in this whole lecture series just unital and associative algebras over a generic field K of characteristic 0. So I'm not studying star structures and not C-star structures. So no norms and no star involutions. This simplifies a bit the formalism. But you can, if you want, also include star structures. C-star structures is more complicated, but star structures you can. And in order to include those, one can work with so-called involutive categories. And I refer you here to this paper we wrote where we explain how to use involutive categories to do what I tell you today, also in a framework where you have star involutions present. So after these preliminaries, I can now state the definition of what an Aqft is. Here I follow the definition given by Brunetti, Fredenhagen, and Ferch, which is an upgrade of the more traditional concept of Aqft as defined by Haag and Kastler. So in the literature, this kind of Aqft I'm defining here is sometimes called locally covariant quantum field theory, but I call that simply an Aqft for, again, notational simplicity. So an Aqft now is the following gadget. It is a functor from the category of spacetimes to the category of algebras. And this functor is supposed to satisfy certain properties, which I will explain in a moment. So how you should think of that functor is the following. So this functor takes in particular every spacetime and assigns to it an algebra. And this algebra A of M you should interpret as the algebra of quantum observables you can measure in that spacetime. Now, if you have a map from a spacetime to another one, the functor gives you a map at the level of algebras, which you can understand as when you have a smaller spacetime sitting in a bigger one, you can interpret observables on the small spacetimes as observables in the big spacetime. So this is what this functor achieves. Now, the properties I'm explaining now, they are motivated by physics, and they, in my opinion, are very natural properties. So the first property is the so-called Einstein causality property, and this is a statement about causally disjoint morphisms. So it states the following. So for every causally disjoint pair, F1, F2, so these are morphisms from M1 to N and from M2 to N to the same target, notice that. Here's the picture. M1 goes to N and M2 goes to N in a causally disjoint way. For each pair of causally disjoint morphisms, the restricted commutator defined here. So this restricted commutator takes observables on M1 and observables on M2, pushes them forward to the big spacetime N, and then forms the commutator on N. And this restricted commutator is 0. So what the Einstein causality axiom tells you then is, in words, that space-like separated observables commute, which is of course a reasonable locality property of quantum field theory. The second property is the so-called time slice axiom, which encodes a kind of time evolution, kind of dynamic law. So how does this go? For every Koshimorphism F from M to N, so remember the Koshimorphisms are those which kind of embed time slabs into a big space-time. So we have a common Cauchy surface here. For each Koshimorphism, the corresponding algebra morphism you get from the functor should be an isomorphism. So this exactly tells you what I was kind of already briefly sketching before, that when you have some observable up here, which in N, which is not localized in the image of M, you can use this time slice axiom in the corresponding time evolution to bring this observable down here to an observable close to the Cauchy surface. So this is indeed kind of dynamic law. Okay, so this is the standard definition, which already appeared in Klaus Vredenhagen's lectures. Let me add a few comments on this definition. And these comments, with this comment, I would like to emphasize the difference between properties. So here, remember, here I emphasized properties, and Aqft is a functor satisfying a list of properties. I would like to emphasize the difference between property and structure. So the previous definition, when you use that, you can define a category of Aqfts as a certain full subcategory of the functor category. So the category of Aqfts is a full subcategory of the category of functors from log to alg. And these functors are selected when they are satisfying the properties 1 and 2, so the properties Einstein causality or time slice axiom. And this definition of the category of Aqfts, of course, gives the correct definition. There's no doubt that this is a good definition. But there are reasons, which I want to explain now, why it is better to encode Einstein causality and the time slice axiom not as properties, so looking at functors and selecting those satisfying a list of properties, but as structure in the framework we use. So number one, it's a more kind of technical reason, is that when you look at properties, it is easy to violate properties by universal constructions. By universal constructions, I, for example, mean colimits. So when you look at colimits of quantum field theories, you might violate the Einstein causality property or the time slice axiom. Another kind of universal construction which might violate the properties are Kahn extensions. So when you extend your quantum field theory from a category to another one, you have no guarantee that you are still satisfying the properties you would like. However, when kind of turning these properties into structure, it gets much better, because when you have additional structure, you can adapt the universal constructions to those which preserve the structure. So structure is easily preserved by universal constructions, while properties are preserved or not, depending on the construction you do. So this is a more kind of theoretical motivation, but there is also a kind of looking ahead towards higher categorical AQFTs and towards gauge theories, which are related to higher categorical structures. There's another, I think, even better reason why one should turn these properties into structures. And this is the following. So in higher category theory, commutativity, so kind of the Einstein causality property, which I've shown you before, is a kind of commutativity property. It's not like saying that the product is commutative, but the product restricted to certain subspaces is commutative. And commutativity, while in ordinary set-based mathematics, people like to understand it as a property, so an algebra is commutative or not. In higher category theory, commutativity is an additional structure. And the relevant buzzword here is that of EN algebras. And if you don't know what an EN algebra is, then you definitely know one example where this feature plays a role. Namely, when you have a monoidal category, so a category with a tensor product, you might want that to be commutative. But in order to kind of witness this commutativity, you need additional structure, which is given by a braiding, kind of interchanging the tensor factors. So, the braiding in a braided monoidal category or in a symmetric monoidal category is an additional structure, which is kind of expressing that this is a commutative tensor product. So, properties are often kind of what people think about properties are often structures, and this becomes clearer when you work in a higher categorical world. So why not doing it immediately right in the one categorical world and implement the properties 1 and 2, so the Einstein causality and the time slice axiom, as structure into AQFT. Now, how to do that for the time slice axiom is relatively easy. You can implement time slice axioms into the structure by localizing your category of spacetimes at all Koshimorphisms. So localization of category means that you add formal inverses for the Koshimorphisms in a kind of universal way. So if you do that, and if you go back and you replace loc in the previous definition by the localized category, you don't have to demand the time slice axiom anymore. Why? Because the time slice axiom is hard-coded by the fact that you are working on the localized category where every Koshimorphism is invertible. So this is an easy trick how to implement the time slice axiom as structure. Now the Einstein causality axiom is more complicated. Why is that so? In contrast to the time slice axiom, so you see the time slice axiom is something which is about a single morphism. Yeah, it is a morphism, and this morphism defines a map from A of M to A of N. So it's a one input, one output condition. For the Einstein causality property, it's a bit different because you see, I mean, here there are 2 inputs and 1 output. So Einstein causality is a condition on a certain binary operation built up from the functor structure and from the algebra structure. So it kind of mixes the functor structure and the algebra structure in a quite funny way, that the condition itself is binary. Now, to implement this Einstein causality as structure, working with normal category theory is not sufficient. You have to kind of have a framework where you can easily work with these binary operations. And there is such a framework, and this is the framework called opera theory. So operats are like categories, however, they also know how to deal with multiple input operations, like the map entering Einstein causality, which is a multiple input operation, 2 inputs, 1 output. Okay, I would like to give a very, very brief definition or introduction to what is an operat and what are algebras over the operat. So if you haven't seen operats before, that might be a bit confusing, but let me help you. So a colored operat, so I'm always thinking about colored operats. So operats with multiple colors. These are a generalization of the ordinary operats, uncolored operats, which you can see in, say, algebraic topology books. But there's an equivalent point of view, which is sometimes useful if you like category theory, namely a colored operat can also be called a multi-category. And what this multi means in category is that a multi-category is something like a category. However, instead of having morphisms with one input and one output, you have morphisms with n inputs and one output. So that is what the multi means. You have morphisms with more inputs. And so n to 1 operations. So these morphisms I call operations in relation to operat. So let me now go through the definition of what is a colored operat. So colored operat, let's call it O, is a list of data satisfying a list of conditions, a list of axioms. So this data is very, very similar to the definition of a category. So let's go through carefully. So number one, in a colored operat, you have a collection of objects, which are denoted by A, B, C, D, etc. with the alphabet. So far, so good. That's as in a category. You have a collection of objects. And in an operat, you also have a collection of objects. Now, what is slightly different is that now in a colored operat, you want that for each tuple of objects. Now here the tuple is bigger. So you see there's a C underline, which means an n tuple of objects, C1 to Cn. So n is arbitrary, so we can do that for all n. For each n tuple of object C and each object T, so for each guy here, you have a set of operations, which are denoted by O, C, T. So these are the operations from tuple C to T. So here's the picture. So these are the operations with multiple inputs and one output. This is the kind of operat analog of the set of morphisms in a category from an object to another object, with the main difference that we have multiple inputs. Now, you want to compose those, yeah? So operations, you want to be able to compose them, and that is done via composition maps. So these composition maps take the operations from A to T, A is a tuple, times the operations from a tuple BI to AI. Now here this goes over all A's, and produces an operation with input the concatenation of all these BI's to T. So in pictures, so this might be hard to read, but in pictures it means the following. So if I have here an operation, this one, of course in order to compose it, I can compose it with many operations here. Yeah, so for each leg here, I can stuff in a new operation. And this is expressed here. So this is the operation up there, and this is the family of operations down there. And composing them means I make here a new big operation out of that. And that, of course, has very many inputs, which is this tuple of B's. Okay, so these are the composition maps. They look slightly different. In a category, composition would be something like that. Would be just linear, but in these operats, it's like multiple input compositions. So in addition to the so similar to the identity morphisms in the category, you would like to have unit elements of those operats. For each object T, you would like to have a unit element, and this is like the operation doing nothing. And there's a new feature which you have for multiple input operations, namely you can permute these inputs. So you can take this input and now start permuting it. And so you would like to have permutation actions. So sigma is an element of the permutation group of n letters. And these permutation actions, they take the operations from C to T to the operations from C permuted to T. So the permutation actions of course, when you permute, you change the order of these tuples, so you permute the tuple as well. And this data I listed here has to satisfy suitable associativity, unitality, and equivariance axioms. So these unit elements should be the units of this composition. The composition should be in a suitable sense associative, which means when I put here more under it and I look at the two possible ways I can compose those, it's the same. And these equivariance axioms tell you how to, when I compose when I permute and compose, that you can take this permutation and pull it through to the very bottom. Yeah? So this is roughly the equivariance axioms. Okay, so this operand now encodes in an abstract way collection of objects and operations between those objects. And to make those operations, to kind of represent them, one uses the concept of an algebra over the operand. So an algebra over an operand is something like a representation of these abstract operations. So let me tell you about the definition in more detail. So if you have an operand O, a colored operand O, then an algebra over O, so A, I call A, with values in a symmetric monoidal category. So algebras take values in a symmetric monoidal category, which I call T, consists of the following data. So to each object of the operand, you assign an object of the category, and for each operations of the operand, you assign a morphism in the category, having exactly the input matches. You see, here this is an operation from C, from the tuple C to T. The T morphism here you get from the algebra grows from the same C tuple, C1, C2, C3 to Cn to T. Yeah. So in this way, the O algebra does something like take those abstract operations and concretely represent them as maps between objects of a symmetric monoidal category. And of course, this assignment here has to be compatible, and compatible in the sense that when I look at compositions and units and permutation actions, then they match with the compositions, units, and permutation actions of the operand. I will not write that out explicitly, but it's like a generalization of the concept of functoriality to the higher arity situation. Okay, now after this definition, let me give you some simple examples. Let me start with one of the simplest examples, which in fact will also be relevant later, and that is the associative operand. So the associative operand AS is an operand which abstractly encodes the operations you have on associative algebras, associative and unital algebras. Now, how to define it with respect to the definition I gave you before? We have to list those 5 data. So the first data is the objects. So the associative operand is kind of, it describes operations on a single object. Yeah. So an associative algebra, there's one vector space with a bunch of operations on them. So this associative operand has just a single object, which I call star. Now, if you have a single object, these sets of operations, they simplify a bit, yeah, because you just have to say from how many to 1 you're looking at the operations. Generically, it was from a tuple C to T, but now all the objects are the same. There's just one object, so I can tell you what are the operations from with n inputs to 1 output, and I don't have to tell you about which objects I'm talking about because there is just one. So this set of operations, which people typically denote by AS_n, so this is the n-ary operations, is given by the permutations on n letters. Later, when I talk about AS algebras, so algebras over the associative operand, it will be clear what these permutations do. Now, composing these operations, composition map has to take a permutation of n letters and compose it with n permutations of ki letters, so k1 to kn. So these are the sizes of these permutations. And how this works is, I don't want to go too much into the details, but it works by kind of multiplying in the permutation group, and which permutations you multiply is once a block permutation, so you make this sigma here into a block permutation controlled by the sizes of the sigma i's, and a sum permutation, so these kind of individual small permutations you sum. So in pictures it is the following. So imagine I would like to look at this composition here. Yeah, so here I have the binary operation which swaps order, so this is given by the transposition permutation, and I want to compose it with 2 more binary operations which also swap order, so again the transposition operation. permutation. So what can I do now here is I can take these dots here and pull them up. Yeah? And when I pull them up, I get here the green bit. The green bit here is now taking two legs and swapping them. This is the block permutation part. And at the bottom, we have the sum of two transpositions. So indeed, this is the picture. So the green part, the sum of the two transpositions, times the block permutation, which permutes the size 2 blocks with each other. The unit operation is the identity element here, and the permutation action is just via the group operation. So this defines the associative opera. Now, what are algebras over this associative opera, and what a surprise, these are the ordinary associative unital algebras, So let's look at algebras with values in the symmetric monoidal category of vector spaces over the field K. Now, when you work out the definition I gave you before, you see that these are precisely associative and unital algebras. And the product in these algebras comes from the 2-to-1 operation, from the binary operation, which you get by evaluating your algebra over the operand on the identity element of the sigma 2 of the permutation group for 2 letters. Yeah? This gives you the product. And the unit of the algebra you get by evaluating your operand algebra A on the unit element of the sigma 0 permutation group. This then is a map from the underlying field to A. Now, how does this relate now to the generic operations labeled by permutations of n letters? So when you have a general permutation, so a general operation in the associative operand, then how this is realized on this associative unital algebra is as follows. So it gives you an operation with n inputs and 1 output on A, and it does the following. It takes a families of A's, A1 to AN, and it multiplies them in the order dictated by the permutation. So you should think of as this permutation, representing an n-to-1 operation, as kind of telling you an order in which you multiply your algebra elements. So this is, I think, relatively easy going. Let me now come to a more complicated example, or a different example, let's not say more complicated, of a colored operand which is of relevance in QFT. So in order to state this example in a sufficient amount of generality, I have to give you a quick definition of a concept which we call orthogonal category. So an orthogonal category is kind of a generalization or an abstraction of what we have seen before, that the category of spacetimes has this perp, which gives us a concept of causal disjointness of pairs of maps, and an orthogonal category is an abstraction of this concept. So an orthogonal category is a pair, C overline, consisting of a category C and a gadget perp, which I say in a moment. So C you should think of as spacetimes, perp you should think of as causally disjoint pairs of maps. Now abstractly in this definition, what is this perp? This perp is a subset of the set of maps, morphisms in the category, to a common target. This is here compactly written as product TT. So you take pairs of morphisms in the category ending up at the same target, at a common target. And this subset here has to satisfy certain conditions. It has to satisfy a symmetry condition. So if F1, F2 is in perp, then F2, F1 is in perp when you swap it. And it has to satisfy a composition stability condition that when you take an element of this subset perp, then when you compose it, so because it goes to the same target, I post-compose it with the same morphism G, and I can pre-compose it with 2 different morphisms, H1, H2, because the pair of morphism goes to the same target, comes from 2 different sources, and I can pre-compose with different maps H1, H2. So if you have an element in perp, then all possible compositions you can do of this form are again in perp. And these conditions are, of course, satisfied for Locke and causal disjointness. Now, for an orthogonal category, what you can do now is you can define an operad which features in quantum field theory, not only in Aqft, but also in other approaches, which I will come back to in a moment. And this operad I call the prefactorization operad, because it first appeared in prefactorization algebras. So the prefactorization operad, PC, this is associated with an orthogonal category. So for each orthogonal category, I can define such an operad. And this operad is given by the following data. So the objects of the operad are precisely the objects of the category. So when you think of the category as a spacetime category, your operad has objects given again by spacetimes. The morphisms, or the operations, the n-area operations in this prefactorization operad are as follows. From a tuple C, C underline means C1, C2 to Cn, to T, the operations are tuples of morphisms in the category. So F1 is a morphism in the category from C1 to T. F2 is a morphism in the category from C2 to T, etc. So it's a tuple of morphism satisfying that Fi is orthogonal to Fj for all I not equal to j. So this is a tuple of mutually orthogonal morphisms. Now these tuples of morphisms you can naturally compose. When you take a tuple and another family of tuples, you can simply compose them in the category. And the identity is just the identity morphism in the category, and the permutation action just changes the order of the tuple of maps. Now, in a quantum field theoretic context, how should you interpret these kind of morphisms, these operations? So you interpret them as follows. So this T here is the big spacetime. So this is the T. And in this T, you have a family of small spacetimes. This is C1, C2, C3. Mapping into that, these embeddings are the Fi's. And these embeddings have the property that they are mutually causally disjoint, so there are no causal curves connecting two different ones. So, so this is the structure of the prefactorization opera. Now the remark, as I already indicated before, this prefactorization opera appeared first in prefactorization algebras, in the sense of Costello and Gwilliam. But in their work, what they used is a specific variant of the prefactorization opera. Namely, they were interested in the case where the category C is the category of open subsets in a manifold, N, so category of open subsets of a manifold, and perp, the orthogonality, is given by disjointness. So disjointness instead of causal disjointness, because Costello and Gwilliam don't work in a Lorentzian setting, they work on topological or Riemannian manifolds, and their causal disjointness doesn't exist because they don't have a Lorentzian metric, so they work with disjointness as orthogonality relation. And disjointness means here the following: if you have a morphism from U1 to V, which is a subset inclusion, and the morphism from U2 to V, then these are orthogonal if and only if U1 intersected U2 is empty. Then for this choice of orthogonal category, this PC I defined before is the operad used for describing factorization algebras in Costello and Gwilliam's works. Okay, now in Aqft, we do something different because we are interested in Lorentzian manifolds and QFTs on Lorentzian manifolds. So we are considering the prefactorization operas on the orthogonal category of Locke, so the orthogonal category Locke of Lorentzian spacetimes, with perp given by causal disjointness, and also on its localization at all Koshimorphisms. And what you get when you do that is quite nice, and this is the content of the theorem here. The theorem says that there exist canonical equivalences of categories, two of them, which I want to explain now in a bit more detail. So the first equivalence of categories is the following. So you consider Aqfts as defined previously, but you forget for the moment about the time slice axiom. So if you study AQFTs without the time slice axiom, this forms a category. And this category is equivalent to the category of algebras over the prefactorization operator. So P-Loc is the prefactorization operator corresponding to the space-time category Loc with its causal disjointness. You consider P-Loc algebras in the symmetric monoidal category of algebras. And the statement here is that this is an equivalence. So AQFTs without time slice can be described equivalently as prefactorization algebras in algebras, where the prefactorization algebras is with respect to Loc. And this description here is equivalent, in a sense, by definition, to algebras over a different operator, prefactorization operator tensor product, the associative operator. This tensor product BV is the so-called Bortmann-Vogt tensor product of operators. And this kind of algebras over this bigger operator, P-Loc times associative operator, you can take in vector spaces. So there are kind of two operators featuring in AQFT, namely the prefactorization operator, but there you have to take algebras with values in the category of associative and unital algebras, or this operator here coming from this Bortmann-Vogt tensor product, and here you take algebras in the category of vector space. Now, you have a similar statement for AQFTs with time slice axiom. So the category of AQFTs with time slice axiom is equivalent to the category of prefactorization algebras, but now with respect to the localization of Loc. So you localize Loc at all Koshimorphisms. So you invert all Koshimorphisms formally. And it's again these algebras with values in the symmetric monoidal category of associative and unital algebras, or equivalently, you can regard that as operator algebras in vect. However, the operator here now is the prefactorization operator corresponding to the localized category Bortmann-Vogt tensor product associative operator. So this is the transition how to go from the traditional definition of AQFTs to the operatic definition of AQFTs. What is useful to understand, in my opinion, is the following. So I emphasized a lot before that it's useful to reinterpret the properties listed in the definition of AQFTs as structure. So it is instructive to see how a P-Loc algebra structure, so this is now a structure, here you see, on this side you have properties, on this side you have structure. So how does the Einstein causality property emerge from a P-Loc algebra structure? How are these related? And that's quite nice, and I like this story, so I'm explaining it carefully. So take any causally disjoint pair of Loc morphisms. So this is a map from M1 to N and a map from M2 to N. These are causally disjoint. Now, for each causally disjoint pair, the P-Loc algebra structure gives you a binary map, which I denote by A, F1, F2, and this goes from AM1 times AM2 to AM. Yeah, this is simply what the operator algebra structure gives you. The pair of maps you can interpret as an operation with two inputs, and the algebra over this operator gives you a way how to realize this operation at the level of the A's. Now, this is not the multiplication of observables in the usual way, because you see this is from M1, this is on M2, and this is on N. So this happens on different spacetimes. So I write this kind of binary operation with a funny product. It is a priori not related to the multiplication of observables in the quantum field theory, which happens on the same M. Now, because let's remember the P-Loc algebra structure, you have P-Loc algebra with values in associative and unital algebras. This means that this map here is an algebra morphism. So it preserves the product and unit of these algebras. All these are associative and unital algebras. Now, what does that mean is I can write out what that means. So if I first multiply in the algebra, so this is a multiplication in the tensor algebra, I have here A1, A2, A1 prime, A2 prime, and then I apply this map, then I get written in terms of the funny product that one. So first multiply on M1 and M2, and then funny multiply the result. And because this map is an algebra morphism, I know it's the same as first funny multiplying A1, A2, and then multiplying it in AN with the associative algebra product with this one, the funny multiplication A1 prime, A2 prime. So written in this way. So you have this identity, which is a consequence of the P-Loc algebra structure in associative algebras. And this identity is the key to kind of compute or to show that you have the Einstein causality axiom. So how does this now go? So Einstein causality requires us to show that taking an observable on M1 and pushing it forward to N with the map F1 and taking an observable in A2 and pushing it forward to N with the map F2, and then multiplying, the order shouldn't matter. So these two things, these two observables here should commute. So this one should be that one. And how do I arrive at the conclusion that they commute? So I realize that these maps here can be obtained from the funny product, namely AF1 on A1 is nothing else but the funny product of A1 with the unit element of A2. And here it's the dot product, the ordinary associative and unital multiplication, and also AF2 small a2, I can realize as the funny product between the unit element and A2. Now I use this relation star here, this identity star, in order to exchange funny and ordinary product. So when I do that, I see that here I get A1 funny star A2. But now using again this relation star, you see that you can write it also in this way, where now the order has changed. This is unit funny star A2, and this is A1 funny star A1. 1. And this is now that. Yeah, so using this compatibility relation, which we got from the structure, we can prove Einstein causality. And this kind of proof is the same proof what you do when in the Ekman-Hilton argument. So this is quite nice, namely that Einstein causality follows from a P-Loc algebra structure via an Ekman-Hilton argument. Okay, so that's quite nice how to see how property emerges from structure. Okay, let me say a few words about the physical interpretation of what I was saying before about this operatic perspective. So the physical interpretation of especially this point of view that Aqfts are P-Loc algebras, so prefactorization algebras with values in algebras. So what that means is that an Aqft comes with two different types of multiplications of quantum observables. On the one hand, you have for each spacetime M, so for each M, you have an associative multiplication on the observables on M. So this is the ordinary operator product. This is how you multiply your operators. But in addition to that, an Aqft has another type of multiplication given by these factorization products. These are the n-ary operations you have in the prefactorization opera. And they are of the following form, so they don't happen on the same spacetime, but they happen from a family of spacetimes, M1, Mn, to a spacetime, to a common bigger spacetime n. So these factorization products are n-ary products, and they change between spacetime. And you have such a factorization product for each picture of this form. When you have a big spacetime and a family of small spacetimes embedding in a mutually causally disjoint way, you have this product for each of those pictures. Now, these factorization products, so they are not operator products, they do something different. And what they are doing is, when I use Klaus Fleetnagen's terminology he used in his lectures, he called those small regions here subsystems. And that's, I think, a good word to use here, because this factorization product is a kind of multiplication operation acting on subsystems. You have like causally disjoint subsystems, and the factorization product tells you how to merge them together to a big system. So this is an operation which is not an operator product, but something coming from this factorization product side. And importantly, the key is that these are compatible. These two types of products. Compatibility is expressed in the statement that that each of these factorization products preserves the algebra structures on the operator products. And this compatibility is the key to understanding Einstein causality as an Ekman-Hilton argument. Okay. So let me say now a few words about how these techniques are useful for universal constructions in Aqft. And the key to that is a result from opera theory, which I want to review here quickly. So a standard result in opera theory tells you the following. If your category, your symmetric monoidal category in which you take algebras in, is bicomplete, so it has limits and colimits, then the following is true. So every colored operad O, for every colored operad O, its category of algebras with values in T is bicomplete. So meaning that independently of the operad, you can take any operad when you take the category of its algebras with values in a bicomplete symmetric monoidal category, you can do limits and colimits of operad algebras. And they result by construction into, again, they produce limits, they produce algebras over the operad. Yeah. So that's good. So it's a bicomplete category, so we can do limits and colimits with operad algebras. Even more importantly, in my opinion, is the following statement. If you have a map of colored operads, so a morphism between colored operads, then what you can do is you can use this morphism to define a pullback functor on the categories of algebras. So this is the P algebras, and this is the O algebra. So you can pull back a P algebra to an O algebra. So this is like the pullback functor when you take a functor from C to D, then you take a functor into C, you can pull it back. Yeah. So this is similar in the world of operads. Now this pullback functor, it has nice properties, namely it admits a left adjoint. So this left adjoint of the pullback functor plays an important role of what I'm going to say later on, and the name for that, these things are typically called operatic left-Kant extensions, because they are the analogs of left-Kant extensions in the world of operads. And how I can use the theorem to do something in QFT is as follows. So I realize that AQFTs are algebras over this operad. So the AQFT operad is the tensor product, Boltzmann-Vogt tensor product of the factorization operad and the associative operad. So this is OC. I have these AQFT operads for every orthogonal category, and hence I have for every orthogonal category a category of AQFTs on C, which is defined as the category of algebras over the AQFT operad with values in vector spaces. Now, because vector spaces, the category of vector spaces, is a bicomplete symmetric monoidal category, I can translate this general theorem up here to a statement about AQFTs. So the statement about AQFTs is the following. So independently of the orthogonal category you're working with, the category of AQFTs is bicomplete. So you can always do limits and colimits for AQFTs, and they result again in AQFTs. So you never violate any properties. B is that if you have any orthogonal functor, so a functor preserving the orthogonality relation on these categories, then you get an adjunction. So the right adjoint is the restriction functor, so you can take AQFTs on the bigger orthogonal category D and pull them back. And the statement is that this has a left adjoint, and this is the operatic left-hand extension. So you have operatic left-hand extensions allowing you to communicate between AQFTs defined on different orthogonal categories. Now, how is that useful? I think a prime example of how this, especially the last statement about these operatic left-hand extensions, is useful is when one would like to formalize a descent condition in AQFT. And let me motivate you why I think descent conditions are useful and nice. So imagine the following practical situation. Imagine that you want to define an AQFT on the category of all spacetimes log, but somehow it's complicated because some spacetimes can have complicated topology, and your construction doesn't work for non-trivial topology. So you kind of just are able to construct the theory when the spacetime has a manifold an underlying manifold diffeomorphic to Rn. So this can happen very well in practical examples, because we know when we look at quantum field theories not on Rn but on generic manifolds, then there are various topological features in them which complicate your construction. So imagine you are in this scenario. You would like to have a theory on all spacetimes, but you just managed to construct one on special spacetimes, on this log diamond. This is a diamond shape, and the diamond means that it has an underlying manifold diffeomorphic to Rn. Now, how can you use these universal constructions to do now something here? So you can restrict the orthogonality relation from the category of spacetimes to the category log diamond. So this clearly goes because this is a subcategory, so I can restrict the orthogonality relation. And what you get is an orthogonal functor. And this functor is the inclusion functor of diamond spacetimes, so simple spacetimes into all spacetimes. And from the previous result, you get an adjunction between the AQFT categories. So here, this is the category of AQFTs on all spacetimes, and this is the category of AQFTs on just the simple, topologically trivial spacetimes. Of course, you have a functor in this way, which tells you if you have a quantum field theory on all spacetimes, you can restrict it to simple spacetimes. That is the easy direction. But the content of the last theorem was that this functor admits a left adjoint. So a functor going in the other direction. So this J shriek here is a kind of extension functor, because it takes a theory which doesn't know about topologically non-trivial manifolds. It is just defined on manifolds of diamond shape. And it extends it in a universal way to a theory defined on all manifolds. Yeah, so this is quite nice. It's an extension functor which you can use to extend the theory which you just know on simple manifolds to all manifolds. Now, this extension restriction adjunction displayed here has some nice properties, namely it exhibits the category of AQFTs on simple spacetimes, on diamond spacetimes, as a full co-reflective subcategory of the category of AQFTs on all spacetimes. So how this sits in here is in a good way, and this good way is expressed here in this co-reflective, full co-reflective subcategory. So this is a concept of category theory, which just means that the unit associated with this adjunction is a natural isomorphism. So the unit is a natural transformation between identity functor and extend and then restrict. So this composition here. Now, what does that mean, this being a natural isomorphism? So this is something happening here. So extend and then restrict. So it means that if you take a theory defined on diamond spacetimes and you extend it and then you restrict it again, you get something out which is isomorphic in a natural way to your input. And this is really an important thing to interpret that as a good extension functor, because an extension functor should have the property that when you extend and then restrict, you didn't change the input. And this is exactly what is formalized here. Yeah, so that is good. So this is really a good extension functor which doesn't change the value of the quantum field theory on diamond spacetimes. And one can now use this adjunction we have here to give a definition of what one means by descent for AQFTs. And this descent condition in words should say something like, it is a quantum field theory on all spacetimes which is fully determined by what it does or what it assigns to diamond spacetimes. So this is what pictorially the descent condition should mean. And we can now formalize that using this adjunction. How to do that? So an AQFT on all spacetimes, an AQFT A on log, satisfies the descent condition with respect to this diamond spacetime inclusion. So descent is always with respect to something. If the corresponding component of the co-unit of this adjunction is an isomorphism. So the co-unit of the adjunction is a natural transformation from restrict extend to identity, and this component of the co-unit should be an isomorphism, and when this is an isomorphism I say that the theory satisfies descent. So what does that now mean? So it means the following. So you have a theory on all spacetimes. You restrict it and then you extend it. So you get another theory on all spacetimes, which however just remembers as input the restriction of A. So this side is a theory which just remembers the behavior of A on diamond spacetimes. And the co-unit being an isomorphism tells you that the theory here, which just remembers the behavior of the theory on diamond spacetimes, is isomorphic to the original theory you start from. So in other words, such a theory A, which satisfies descent, is fully determined by its values on diamond spacetimes, and that is nice. That is what we wanted to formalize. And let me give you an example. So the free scalar field satisfies this descent condition. That's quite complicated to prove. That was the content of the PhD thesis of Benjamin Lang from York previously. So the free scalar field satisfies this descent condition, but gauge theories do not satisfy this descent condition in this particular form. The reason is that this descent condition here is a one-categorical condition, while gauge theories behave higher categorically. And in the next lecture, so in lecture 2, I will show you, I will introduce a higher categorical generalization of the descent condition that applies to gauge theories, and I will verify it in simple examples. Better say toy models. Okay, let me now conclude. I'm pretty much over time. Summary. So I spent quite some time to explain that AQFTs admit, and in my opinion quite elegant description, as algebras over colored operats. These colored operat OC we call the AQFT operats. These AQFT operats are related to prefactorization operats, and yeah. So this is a quite nice point of view, and this reformulation is not just kind of elegant or when you like your opera theory that you enjoy, but it also has practical advantages. So this reformulation in terms of operats turns the Einstein causality and time slice axioms from properties into structure. And that has advantages. Some of them of theoretical, some of them of practical nature. So the first advantage is that from this structural perspective on Einstein causality, you see that Einstein causality comes from an additional structure. It's a consequence of an additional structure via an Ekman-Hilton argument, which is an argument kind of saying that when two multiplications behave well with respect to each other, they are commutative. And this is here the same. So that's quite nice to have a more conceptual point of view on Einstein causality than just implementing it as a property or demanding it as a property. Now, from a more practical point of view, the nice thing about opera theory is that you get these universal constructions and you don't have to worry about that they violate the Aqft axioms. The Aqft axioms are hard-coded in the structure. So all these universal constructions I was talking about preserve by construction. These are Aqft axioms, so that is quite nice. And furthermore, this operatic point of view is the right starting point for discussing higher categorical generalizations of Aqft, which I do in lecture 2. Now, a particularly interesting universal construction is the extension-restriction adjunction I discussed in some detail. And this extension-restriction adjunction is the following. It goes from Aqfts on all spacetimes, log. It goes between Aqfts on all spacetimes and Aqfts on diamond spacetimes, so spacetimes whose underlying manifold is just Rm. And we have two functors, so in adjunction always two functors. We have the easy one, restriction functor, restricting an Aqft to an Aqft on just diamonds, and the more interesting extension functor. And this extension functor by construction preserves all the Aqft axioms, so you don't have to worry about that when you extend your theory. So this extension functor here has some relationship to Fredenhagen's universal algebra, which was kind of a non-operatic approach with a kind of similar inspiration for taking a theory on some special spacetimes and extending it to all spacetimes. But Fredenhagen's universal algebra construction had this problem that the output is not necessarily an Aqft, and this is refined in our approach. And furthermore, this extension functor here is structurally very similar to factorization, which people do in topological QFTs. With factorization homology, that would be the category of manifolds, and that would be the category of disks, and factorization homology is a kind of extension of topological QFTs from disks to manifolds. And this is the Lorentzian version of such a construction. Okay, thanks a lot.